Hi everybody and welcome to another video of the Optimization Masterclass. So this class is going to be based on the course that I do at Imperial College, which is based on this book, Convex Optimization, of Stephen Boyd and Lieven Vandenberger. If you haven't followed the previous lectures in this series, please check the link over here. Remember that you can download the material that I use to teach the class, so the so-called smart handouts, from the link in the description down below. If you have suggestions on future topics that you would like that I cover in this masterclass, please leave it in the comments below. Thank you very much and enjoy the course. Okay, the next topic that we're going to cover is that of generalized inequalities. Generalized inequalities are quite an interesting topic, and they're quite important for two reasons. One is that they allow us to formulate and then solve quite complex convex optimization problems. And also, generalized inequalities are the way to actually make sense of multi-objective optimization problems in a mathematical way, so in a proper way, essentially. So let's go and try to understand what we mean by generalized inequalities. Well, the basic idea is that we want to generalize the concept of less equal or greater than equal with respect to something that is more general than positive versus negative. Okay, so let's see how to do this. So we consider a cone K. Okay, so we know what a cone here is, and then we define the concept of proper cone. Okay, so a cone K is a proper cone if it is convex, it's closed, so that means that it contains its boundary. It's solid, that means that it has a non-empty interior, and then it's pointed. Okay, pointed means that it contains no line. So what does it mean? So essentially it means that it has a tip. Okay, so for instance, the non-negative Orthant, which is essentially all the all the x which are positive in all the components, it's a proper cone. Okay, it's convex, is closed, is solid because we are of course considering all the elements inside and the boundary, and is pointed because it has a tip. If we instead we consider a line, well, we know that a line is an example of cone as long as the zero element belongs to the line, but it's not pointed, okay, because it doesn't have a tip. Okay, so yeah, these are two examples. If we have a proper cone, then we can define generalized inequalities. Now, let's go through the definitions. And then there's going to be a picture that is illustrating the meaning of these and some example, and everything will be more clear. Okay, so if we have a cone K, okay, we can associate a partial ordering on the real numbers, on the real vectors, okay, which is defined in the following way: x is less or equal than y with respect to the proper cone K, if and only if y minus x belongs to the cone. And we can also define a strict version of it: x is less than y with respect to the cone K, if and only if y minus x belongs to the interior of K. In a similar way, we can define greater equal and strictly greater with respect to the cone K. Okay, of course, when the cone K is just R plus, then we have the standard ordering. So essentially, this symbol reduces to less equal on R. Okay, so the normal inequality. Two basic example of generalized inequalities are the ones that are defined on the non-negative Orthant and on the positive semi-definite cone. Okay, so let's look at the first one. So if we take the cone R plus and power n, which is the non-negative Orthant, then of course this is a proper cone. I just made it as an example above, and the associated inequality corresponds essentially to the component-wise inequality between two vectors, because essentially what you are requiring is that all the components of the vector are going to be positive, as I explained above. And this type of generalized inequality is very, very common, I mean, with respect to R+, and that for that reason we just indicate it without without the k at the bottom, or without the R+ at the bottom. So whenever you see this symbol, that up to this point we called component-wise inequality when we were comparing two vectors, that's nothing else that the generalized inequality with respect to the non-negative Orthant. Similarly, if we consider the cone of positive semi-definite matrices, which is S plus power n, this is going to be a proper cone. We have a picture above. You can see that is pointed. It's solid. And so on, so it is convex and so on, so it's a proper cone. And the associated inequality essentially means that if x is less or equal than y in the respect to the cone S plus, that means that y minus x is positive semi-definite. And this, it's a very common operation, and then again we drop the subscript k when we say essentially that a matrix S is less or equal than y. We mean that this less equal is with respect to the proper cone, which is the cone of positive semi-definite matrices. Okay, which is, we know that this means essentially that x minus y has to be positive semi-definite. Okay, so the point of defining generalized inequalities in this way is because, of course, many of the properties and intuition that there is behind classical standard inequalities apply also in this case. We will see, however, that some things instead do not extend to generalized inequalities. So first of all, let's look at some properties that we know they work for standard inequalities, and they work also for generalized inequalities. Okay. So let's look at some examples. The inequality, the non-strict inequality, is preserved under addition. So if we have that x is less than y and u is less than v, then x plus u is less than y plus v. The generalized inequality is transitive. So if x is less than y and y is less than z, then x is less than z. The generalized inequality is preserved under non-negative scaling. That means that if x is less than y and we have a non-negative factor alpha, then alpha x is less or equal than alpha y. The generalized inequality is reflexive, so x is less or equal than itself. Is antisymmetric, which means that if x is less than y and y is less than x, then they are the same element. And is also preserved under limits, which means that if we have an infinite number of xi's and yi's, which all obey the relation xi is less equal than yi, and we have that xi converges to a limit x and yi converges to a limit y, then also the limit satisfy the relation that x is less equal than y. For the corresponding strict inequality, again we have some standard properties, which are that if x is less than y, then x is less or equal than y. We have that if we have x less than y and u less or equal than v, if we sum them, we have that x plus u is less strictly than y plus v. We have that x less than y is preserved by positive scaling. We don't, x is not less than itself. Okay, so that's what it means. This property means. And finally, we also have that if x is less than y, we can add a small quantity, the same small quantity, both in x and y. And for small, actually two different quantities, for small enough quantities, we still have the same inequality. So the inequality is preserved for very small additions on both members. So as I said, the notation that we're using is meant to recall the standard notation because a lot of properties of standard inequalities hold for generalized inequalities. But there are some differences. Now we look at the differences, which are actually quite interesting. The most important difference is that the standard inequality less equal is a linear ordering, which means essentially that any 2 points are comparable using this inequality. That means that if I give you an x and a y, it's either that x is less equal than y or y is less equal than x. Okay, you cannot say that you cannot compare them. You can always do that. This is not true for generalized inequalities. For generalized inequalities, there may be elements which are not comparable, and this has a consequence which is very relevant for optimization, which is the fact that we can distinguish 2 different types of optimality. And we can distinguish in particular between something that we call a minimum and something that we call a minimal element of a set. So let's look at the 2 differences. So we say that given a set S, X is a minimum of that set if for every other element Y belongs to the same set, X is less or equal than Y. Okay, and this implies that the set, if the set has a minimum element, that element is unique. Okay, and this is different from a minimal element. So let's consider X belonging to the set S. X is a minimal element if taken a Y, okay, such that y is less or equal than x, then this implies that y is equal to x. Okay, so for the standard inequality, if you try these 2 definitions, they're going to give you the same element. However, for generalized inequalities, this is not the case, and the importance is here. Okay, is the fact that it is here. Okay, is in this condition. In the minimal definition, what we say is that if a y belonging to the set is less or equal than x, this implies that y is equal to x. So what is important here is that there may be y's belonging to S that are not comparable to x. Okay, and this cannot be the case for the minimum element, because for the minimum element we need to be able to compare all y's. Okay, so this is the key difference. For the minimum element we have to compare all y's and our x has to be smaller than all the y's. For the minimal elements we don't need to compare the all y's, but whenever we can compare it, then that has to be if we can compare it and the element we compare is actually less or equal than x, that implies that it has to be equal to x. Okay, let's look at a geometric definition which looks even more complicated than and more confusing than what we just stated, but then if we look at the picture, everything will make sense. So the definitions that we are just given can be formulated in a geometric way in the following way. Okay, a point x is a minimum of S if and only if S belongs to the set x plus k, where x plus k denotes all the points that are comparable to x and they are greater than or equal than x, according to the generalized inequality. While a point x is a minimal element if and only if the intersection of x minus k and S is the singleton x, where x minus k denotes all the points that are comparable to x and less than or equal to x. Okay, so before it was greater and now it's less. Okay, I'm sure that this is very confusing. Let's look at a picture because this will clarify things very easily. So we have 2 sets S here and 2 sets S, okay? And in one case, we can identify a minimum point with respect to the standard generalized inequality. And in the other case, we can identify minimal points, okay? Here we are using as a proper cone the non-negative Orthant, so R plus. Okay, and okay, of course we are in the plane, so this is R plus 2. Okay, and we know that this cone is essentially, you know, if we trace it, is this set over here. Okay, now what the definition of minimum element is the following, is given here. Okay, S needs to be included in X plus K. If we do X plus K, well, X plus K is nothing else that this all set here, because it's the negative Orthant shifted, translated, so that the origin, the point 0, now is x1. So this is the translated negative Orthant, and is x1 plus k, and it contains the entirety of S. Okay, and this confirms that x1 is a minimum. Of course, if you, for instance, put yourself here, okay, and you ask, let's call this point here x bar, and we put here, you know, we move the negative, the non-negative, if I said negative Orthant, I meant non-negative Orthant. The non-negative Orthant here, you see that, I mean, x bar plus k does not contain the entire set, and that means that x bar is not a minimum point. Okay, so you see that this actually works. It's surprising, but it actually works. Now let's look at the definition of minimal element. So we need to take x minus k, and in this case x minus k is going, with respect to x2, is going to be this set over here. Of course, because minus k in the case of the positive of the non-negative Orthant is going to be the non-positive Orthant, so it's going to be essentially this guy over here. Okay, and x2 is going to translate the origin such that this point is going to be x2 instead of being 0. And the condition is that if we do the intersection between x2 minus k and s, we need to get as a result x2, and this is the case. Okay, this x2 is the only point there. But of course, this x2 is not unique. I mean, this minimal point is not unique. If I put myself here, then you see that with respect to, you know, and I trace, let's call this x double bar. Well, this is x double bar minus k, this set here. You see that the intersection with s is just x double bar, so that x double bar is a minimal point. Okay, so you see that there are a lot of minimal points here. In particular, all the points that are here on this line are the minimal points, and in a certain way they are optimal, they are minimal, okay, because in this sense that we have defined, I mean, we understand from an intuitive point of view that with respect to you know, a sort of scale of value that tell us that this is big and this is low, we see that these points on the left hand side over here on this line here are small in a certain way, are minimal in a certain way, but they cannot be isolated using the classical definition. Because this point and this point are not comparable with respect to each other. Okay, so if I remove all this stuff and I build and I try to check, for instance, you know, put the x plus k here, you see that you know, this simply doesn't work. I mean, this x plus k does not contain, wherever I put it, you know, wherever I put it, I can put it wherever I want, is never going to include the whole set S. Okay, so this set S cannot have a minimum point, but still we have this concept of minimal points, which allow us essentially to still find certain points which are special among all these points. Okay, and as I said, this is an important concept when we look at convex optimization problems or general optimization problems with multiple objectives. We have already seen in some examples that in those problems we don't have a minimum point, but we will have multiple minimal points, which are actually Pareto-optimal points. So we will define this properly in the next lectures, but the basic idea is essentially here. Okay, when we have multiple objectives which cannot be compared, then instead of looking at minimum, so the best in absolute, we need to look at points which are the best in, let's say, relative terms, which are minimal points. In this section, we're going to cover the topic of separating and supporting hyperplanes. The objective of this section is essentially to introduce the idea that we can use hyperplanes to characterize convex sets. And this is useful then for the following section, which is about dual cones and generalized inequalities based on the dual cones, which actually is a quite complex topic from a mathematical point of view, probably one of the most complex that we will see, but it's actually very useful to characterize minimum and minimal elements from a geometric point of view. So let's start now with this idea of hyperplanes, and we will look essentially at two theorems. The first one is called the Separating Hyperplane theorem, and it says the following, okay? So we consider two sets, C and D, which are non-empty, they are disjoint, and they are convex, okay? Then this implies that there exists a separating hyperplane. What is a separating hyperplane? Well, the implication is essentially that there exists an A and there exists a B, okay? Such that for all the points in one of the two sets, so for instance the set C, then A transpose X is less equal than B, and for all the points in D, A transpose X is greater or equal than B, okay? So this essentially means that the hyperplane defined by all the points X such that A transpose X equal to B is separating the sets C and D. So essentially all the points of D lies in one hyperspace associated to the hyperplane, and all the points of C lie in the other hyperspace associated to the hyperplane. Okay, it's important here to stress that actually the separating hyperplane theorem holds true only when we are considering the non-strict inequality. In fact, it's not true that the theorem holds in general for the strict inequality. Of course, the picture that we have here, of course, is an example in which the separating hyperplane theorem holds for the strict inequality. But what I'm saying is that it's not true in general that if I give you a C and D, which are non-empty, disjoint, and convex, then there is a separating hyperplane strict that gives strict separation, essentially with the strict inequality. For instance, an example of such a set that is separated by a non-strict separation, it's a set C, which is a convex set which has its boundary. Okay, so it's a closed set, and then we take a point D here. Okay. And the set associated to that point, so a singleton, so we take a set which is a singleton made of just that point on the boundary, which we call D. Now we see that, of course, the separating hyperplane theorem says that we can construct a hyperplane such that all the points of C are in one of the half spaces, for instance, the one that's satisfied with the less equal. And then we see that all the points of D, which is in this case just 1 point, satisfy that it's going to be in the other half space, which is going to be for the greater equal, satisfy the inequality for the greater equal. But of course, it's not, it actually satisfied for the equal and not for the greater equal for the equal, so that means essentially that it's not satisfied strictly. So this is to say that in general, there is not strict separation, but just separation, and that means that the two sets, even if disjoint, may actually touch. There is some type of converse for the separating hyperplane theorem, but just the standard converse, so just using exactly the same condition, does not hold. Okay, what do we mean by converse? Well, we mean that it's not true that if you are given two sets and you can find a separating hyperplane, that if you're given two convex sets and you can find a separating hyperplane, it's not true that this implies that C and D do not intersect. And as a counterexample, we can consider the set C and the set D, which are made just of one element, a singleton. And then you see that the separating hyperplane, sorry, we were given C and we were given D, okay, which is made just by a singleton. And we know that C and D are convex, okay? And we can construct a separating hyperplane because an hyperplane passing through 0 will satisfy the less equal, for instance, for C, and the greater equal for D. Of course, in both cases are actually satisfied with the equality, but the condition is satisfied, that's the point. So we found a separating hyperplane, but of course C and D are not, are intersecting, okay? So the intersection is not empty, okay? So the converse is not true. Unless we add additional conditions. So if we add additional conditions, then the separating hyperplane, the existence of a separating hyperplane implies the fact that C and D are disjoint, okay? And as an example, we can now look at a set C, which does not now have the boundary, so it's an open set. And now you see that, actually, let's just look at this example that I constructed over here. If now C does not include the boundary, you see that the separating hyperplane that we have here is actually implying that C and D are disjoints, okay? So this is to say that it's possible to add additional condition in such a way that the converse of the separating hyperplane holds. For instance, any two convex sets C and D, where at least one is open, are disjoint if and only if there exists a separating hyperplane. Okay. A concept which is very close to that of separating hyperplane is that of supporting hyperplane. And so let's look at the definition. Okay. So we consider a set C, and then we consider a point x0 which is on the boundary of C, okay? Then if there exists an A such that A transpose X is less equal than A transpose X0 for all X belonging to C, then we say that the hyperplane defined by A transpose X equal to A transpose X0 is called a supporting hyperplane, okay? So what is, from an intuitive point of view, a supporting hyperplane? Well, the idea is the following. Given a set C, okay, and you can take any type of set, if you take a point on the boundary, okay, and you construct, you're able to construct an hyperplane passing to that point, such that all the set C lies on one side of the hyperplane, that's a supporting hyperplane, okay? So for instance, if I take this point here and I trace this hyperplane, that's another supporting hyperplane because all the set is lying on one side. If I take this point here, well, you see that this is not going to be a supporting hyperplane because the hyperplane is cutting through the set. So actually this is suggesting already the fact that the convexity has to do with the existence or not of supporting hyperplanes at every possible point. Because you see that if we are in a in an area that is convex, then it's easy to construct a supporting hyperplane. But if we are in an area in which there is no convexity, then it's impossible to construct a supporting hyperplane. And actually, it's interesting. I want just to point out that an equation of this type is something that we saw already before, and essentially, if you remember, it means that if we take a point x on the hyperplane and we consider the vector starting from x0 to x, then what we have is that the scalar product between x minus x0 is going to be 0, okay? So because the angle is 90 degrees. And then the condition for the supporting hyperplane, which is essentially the x transpose x is less equal than x transpose x0, simply means that essentially all the possible vectors that can be constructed in C, okay, are actually have an angle which is bigger than 90 degrees. Okay, so this is a concept that we saw before, and I wanted to point out that similar interpretation in terms of angles and the scalar product can be done. So here, I mean, the point is that a basic result it's the supporting hyperplane theorem, okay, which essentially says that if you have any non-empty convex sets, set C, okay, and you take any point on the boundary, then there exists a supporting hyperplane to C at x0, okay? So that means essentially that if you have a convex set, you can construct a supporting hyperplane at any point of the boundary, okay? And this is nothing else than an application of the separating hyperplane to the two sets C and the singleton X on the boundary, okay? There is some partial converse of the supporting hyperplane theorem, and again, in general, the converse of these theorems do not hold unless we add additional conditions. And here, one formulation of the converse, because again, at the moment in which we add additional conditions, we have a choice of what conditions to add. One possible converse is the following, that if a set is closed as non-empty interior and has a supporting hyperplane at every point of its boundary, then this implies that it's convex. We now reach the last section of this chapter, which is about dual cones and generalized inequalities associated to the dual cones. So this is going to be a quite difficult topic from a mathematical point of view, and my suggestion is always to try to think of these definitions from a geometric point of view, try to do some pictures in the plane, because I mean, once you do the pictures in the plane, these things starts to make sense. So let's consider a cone K, and then we define what is known as the dual cone of K. The dual cone of K is indicated with the K star, and is made of all the points Y that satisfy this condition, essentially all the points that have a non-negative inner product with all the elements of the cone K. As the name suggests, a dual cone is a cone, okay? And what is interesting is that a dual cone is always convex, even though the original cone is not convex, okay? And actually we will say a bit more about this in a moment. A geometric characterization of this condition is the following. Y belongs to the dual cone if and only if minus y is the other normal of an hyperplane that supports K at the origin. What does that mean? So let's consider a cone K here, that is given over here. Okay, so if we want to check if y belongs or not to the dual cone, we consider the normal y associated to this hyperplane, okay? And we see, I mean, that by the definition, the inner product between any points in K, so for instance, let's consider this point, and then we take the associated vector x, then the inner product between x and y is going to be non-negative, okay? And that implies essentially that the y isn't the dual cone, but here the point is to look at the geometric characterization. The geometric characterization is that if y belongs to the dual cone, then there exists a supporting hyperplane associated to that y. It's not the case if the point does not belong to the dual cone. For instance, if we take this z now and we construct the hyperplane associated to the z, we see that this hyperplane is not a supporting hyperplane because it's cutting through the cone K. And in fact, what happens is that if we try to compute the inner product with all the points in K, we will find some that violate this condition. Of course, if we take the point x here, the condition is going to be satisfied because the inner product is going to be non-negative. But the point is that you have to satisfy this for all x in K. And so if we take a point over here and we take this vector, So since the angle between this point, let's say x bar and z is greater than 90 degrees, then the inner product is not going to be non-negative. Okay, so essentially this is the geometric characterization. The geometric characterization tells us that if a point belongs to the dual cone, then we can construct an hyperplane that is supporting the cone, okay, the original cone. Dual cones have the following properties. So as we said, a dual cone is always convex and actually is also always closed. So it doesn't matter what you start with. It doesn't matter if the cone K is convex or not, or closed or not. K star is always going to be closed and convex. And there is the property that if the cone K1 is smaller, so is contained in K2, then the opposite happens for the dual cones. This essentially implies that a small cone will have a very large dual cone, and a large cone will have a small dual cone. Okay. If K has a non-empty interior, then K star is pointed, okay, which we should remember it means that it has a tip. And the opposite is actually can be relaxed, okay? In particular, if the closure of K is pointed, then K star has a non-empty interior. So you have to realize that this is a relaxation, not a restriction, okay? Essentially, we're saying that K does not have to be pointed, okay? But if the closure of K, which is actually something that it's bigger than K, is pointed, so even if K is not pointed, as long as the closure of K is pointed, then K star has an empty interior. So in one direction, again, the properties are better, let's say, okay? So we already saw this here, the fact that K star is always closed and is always convex, okay, even though the original K is not. And in particular, I mean, the main point here, I mean, the reason why there is no symmetry between these properties is exactly because the K star is always closed and is always convex. And the reason why this is the case is the following, and we can see it here. If we try to compute K double star, so we take a cone K, we find the dual, and then we find the dual of the dual, we're going to get is not K, but it's actually the closure of the convex hull of K, okay? So this is essentially what taking the dual does, okay? So that means, however, that if we start with a K that is convex and is closed, then the double dual is actually the original set, okay, the original cone. But if K is not convex and is not closed, by taking twice the dual, we actually construct the closure of the convex hull of K. Finally, if K is a proper cone, then also K star and K double star is going to be a proper cone. And this is, I mean, this is implied by all the properties that we saw before, okay? And the fact that K star is always closed, is always convex, and so on, okay? As an example, we can look at the cone R plus power n, and R plus power n is self-dual, okay? That means that essentially that the dual is itself. Why this is the case? Well, I mean, the proof is very simple, okay? So we can see that x transpose y is greater or equal than 0 for all x which is greater or equal than 0 in the inequality associated to R plus. Well, if and only if also y is greater or equal than 0 in the inequality associated to R plus, so the component y is inequality. Of course, because if you know, if we take a y that doesn't have all the components non-negative, let's say that for instance one of the components of y is negative, then since this stuff has to hold for all x, well, we can find an x that is going to weight the negative component of y a lot, and all the other components are taken as 0 in x. You can do that. And then this inequality is not going to be satisfied, okay? So that's the simple proof. Another example is about the positive semi-definite cone. So I recall again that the positive semi-definite cone S plus behaves in the same ways as R plus. Okay, so we know that R plus is self-dual. Well, it happens that S plus is self-dual as well. Okay, and of course we have to define the inner product for this cone, and the inner product for the cone is defined in this way. Okay, so if X and Y are two positive semi-definite matrices, then the inner product is defined as the trace of the product, which essentially is just the sum of all the products between all the components of the two matrices. So that means essentially that S plus is self-dual, means that if the trace of xy is greater than or equal than 0 for all x positive semi-definite, this implies, it is implied as well, so it's if and only if, y is again a positive semi-definite matrix. Okay, and the proof of this is left as an exercise. You remember that if the convex cone K is proper, then this induces a generalized inequality that we indicate in this way. Okay. Well, if the dual cone is proper, then also the dual cone induces a generalized inequality, which we indicate in a similar way. Okay, and there are some properties of the relate the generalized inequality with respect to K and the generalized inequality with respect to K star, and we look at these two properties. Okay, they are the same actually. Okay, so just let's look at the first one. The first one says essentially that if we have that x is less equal than y with respect to K, then this is true if and only if this is also true. Okay, that lambda transpose x is less equal than lambda transpose y for all lambda transpose which are positive in non-negative in the dual inequality. Okay, so what is the point here? I mean, here the point is that there are two things to notice. Okay, so first, this condition here is nothing else than the generalization of something that it's very simple. The fact that if you have that x is less equal than y, okay, then if you have an alpha which is greater or equal than 0, then alpha x is less equal than alpha y. Okay, so this is a generalization in two directions because it generalized to vectors, but then it generalized with respect not to the standard inequality, but actually to a general inequality K. Okay, and here the important thing is that something that you don't know, I mean you don't see in this case, is the fact that these two inequalities are actually different. Okay, one is the inequality with respect to one cone, and the other one is an inequality with respect to the dual cone. Okay, the reason why they are the same is because, of course, for scalar and actually also for component-wise inequalities, just for standard vectors, the two inequalities are the same because the two cones are the same. Okay, but for essentially more in general, the thing to notice is the fact that if you want to have this kind of properties, then the lambda vector has to be in positive or better non-negative with respect to the dual cone K. There is also another interesting aspect to point out in this condition, and it's the fact that essentially we can compare, there is a way of comparing elements with respect to one inequality and elements with respect to the other inequality that transforms the comparison in a comparison with respect to the standard inequality less equal than something, okay, which is essentially just a scalar inequality. Okay, so essentially we can compare, there is a way of comparing vectors that belongs to the normal cone and dual cone in a way that it's just a comparison between two scalars. And this is actually something that will arise again when we will look at the KKT conditions of optimality for our problem, when we want to generalize those conditions to generalized inequalities. We will see that one of the KKT conditions actually it's based on this concept of cone and dual cone. But now actually we already have an application which is very important, and the fact that dual generalized inequalities can be used to characterize the minimum and the minimal element of a set S. Okay, so let's look at the mathematical definition, and then we have a picture here to explain what this means. Okay, so X is the minimum element of S with respect to the generalized inequality induced by K, if and only if for all lambda which are strictly positive in the dual cone, X is the unique minimizer of lambda transpose Z over all the elements belonging to S. Okay, so geometrically this means that for any strictly positive lambda, the hyperplane, which is defined in the following way, okay, so lambda transpose times Z minus X equal to 0, is a strict supporting hyperplane to S. Okay, where here by strict supporting hyperplane we mean an hyperplane that intersect S only at one point X. Okay, and note that in all this definition we didn't use convexity, so this is true always. Okay, so I'm sure that this is very confusing up to this point, so let's try to understand what this means. Okay, so we have our consider this cone, this set S, okay, that is shaped a bit as a cone, so that it's easier to represent the geometric meaning. Okay, so we want to look now at the minimizers of lambda Z. So what does it mean? Well, let's consider, for instance, this hyperplane. Okay, so this is the hyperplane lambda transpose Z. Okay, and then we want to minimize it. Okay, so how do we minimize it with respect over the Z belonging to S? Well, of course, I mean, if we are minimizing with respect to okay, we also need to specify the cone here, otherwise we don't know what that means. In this case, we are minimizing with respect to the cone K, which is R plus, okay, squared. And so that means that if we want to minimize this hyperplane with respect to the points of S, with respect to the R plus cone, then it means that we want to push this hyperplane in this direction, because as we move it in this direction, we are minimizing with respect to this cone. Okay, so we push, and we end up with this hyperplane here, and we see that this is the unique minimizer of this minimization. Okay, and now the point is that we can do this with another hyperplane. So let's consider now this hyperplane, which is, for instance, lambda bar transpose Z, and we do the same. If we do the same, we end up with this hyperplane, which again has a unique minimizer, which is the same point. And we do this, I mean, we repeat this with all possible lambdas, okay? So that's in the definition, okay? So this has to hold for all lambdas which are positive in the dual norm, okay? And of course, since we are here in R plus, we know that the dual cone is the dual cone is, I said dual norm here, but I meant dual inequality. So we are in R plus, so we know that the dual cone is again R plus. So essentially we're saying for all the lambdas that are component-wise strictly positive, okay? And so a vector that is component-wise strictly positive is essentially associated to this type of hyperplanes, okay? And the point is that we have to push all of them in that direction, and I'm going to end up with just this point, and that's going to be the unique minimizer of all these bundles once we push them, and so we get all these type of hyperplanes. All these are supporting hyperplanes, and this implies that this is a minimum element. We now look at characterization of minimal element, again with respect to generalized inequalities. So X is a minimal element of S with respect to the generalized inequality induced by K if taken as strictly positive lambda with respect to the dual cone, X minimize lambda transpose Z over Z. Okay. Now, what are the differences with respect to before? Well, the difference with respect to before is that we're not requiring that X is the unique minimizer of this expression. Okay. It just have to be one minimizer with respect to one lambda, essentially. If we take a different lambda and we find a different minimizer, that's going to be a different minimal point. Okay, so that's the key. So the key here is that, for instance, if we take this hyperplane associated to lambda 1, and then again we are minimizing with respect to the cone R plus, okay, so the component-wise inequality, and again the dual inequality here is associated to again R plus. So if we're minimizing here, it means to push this hyperplane in this direction, and we're going to end up with selecting, with a minimizer, which is this point over here, that minimize this specific lambda z. Okay, so this is essentially the hyperplane associated to lambda transpose z. Okay. Of course, if we take a different lambda, so in this case lambda 2, and now we minimize again with respect to R plus, we are going to end up with, so sorry, my sketch here is not great, but you know what I mean. I mean, if I take lambda 2 here, and I'm going to minimize it with respect to R plus, I'm going to find again one minimizer over here. The key point here is that x1 and x2 are not the same, okay? So they still minimize with respect to one specific lambda. They do not minimize with respect to all lambdas. So this is the minimizer with respect to lambda 1, but it's not the minimizer with respect to lambda 2. So the x1 is not going to be a minimum. It would be a minimum if x1 minimizes with respect to all lambdas, but it doesn't, okay? Because obviously, if we look at lambda 2 and we look at the when lambda 2 passes through x1, we see that we can still do better. We can still go down to x2, and x2 is going to be the minimizer in that case, and that's why x2 is going to be the minimal element, another minimal element. And so by repeating this with all lambdas, okay, we can find a lot of minimal points. One important thing to realize though is that, okay, we have to be careful here, okay? So this is very tricky, and you have to pay a lot of attention. So first of all, the definition with minimal is just a sufficient condition, and this is different with respect to the minimum definition. In the minimum definition, we have if and only if. So if and only if this is true, then x is a minimum. In this case, this is just sufficient. So that means that if you find an x that minimizes lambda transpose z, great, that's going to be a minimal point. But not all minimal points are identifiable in this way, okay? Maybe you're already thinking back to the definition of Pareto-optimality and something that we discussed already, and the fact that, when we try to minimize, we optimize a multi-objective function, we variate the weights, and we can find a lot of Pareto-optimal points in this way, but we will not find all of them. And this is exactly the reason why, and it will be clear in a moment, okay? But yeah, I mean, the point here is that using this definition, this is just a sufficient condition. So we will find a lot of points, minimal points in this way, but we don't have the guarantee of finding all minimal points. And here there is a nice counterexample, okay? So if we have this set, we see that this point is minimal with respect to r plus square, okay? And this is using the definition that we saw before. It's the fact that, we have k, which is r plus square, and this is the set x minus k. And we see that if we remember the definition of minimal point, a point is minimal if x minus k intersected with s gives you just the element x. Okay, so this is the case here. So x is a minimal point, but there exists no supporting hyperplane here. Okay, so you see that if I trace this hyperplane, this is not a supporting hyperplane. If I trace it this one, this is not a supporting hyperplane because it's cutting through S, right? So whatever plane I put is never going to be a supporting hyperplane because it cuts through S. One can create Converse statements by increasing the number of assumptions. Okay, so we can create statements in which we can find the more we can find minimal points characterized in exactly in that way by increasing the number of assumptions. Okay, for instance, if S is convex, and you remember that up to this point we didn't assume that S was convex. So if S is convex, then for any minimal point x, there exists a non-zero lambda greater or equal than 0 in the dual inequality, such that x minimize lambda transpose z. So what are the differences with respect to before? So the difference is that we now assume that S is convex, and before we didn't. Okay, but there is something that we need to stress here, is the fact that this is not a perfect converse because this inequality is not strict. So if we look back at how we defined this this definition, lambda was supposed to be strictly positive, both in the minimum definition and in the minimal definition. Here, for this partial converse, lambda is actually greater equal than 0. Okay, this is important because this converse cannot be strengthened to lambda strictly positive. Okay, so there are examples that shows that x can be a minimal point of a convex set S, but not a minimizer of lambda transpose z for lambda strictly positive in the dual inequality. Okay, of course it's going to be true for the non-strict inequality because that's exactly what we stated 1 second ago, but not for it doesn't hold for the strict inequality. Okay, and it's not true also that any minimizer of lambda transpose z with this condition is minimal. So again, the converse of the converse with the strict inequality does not hold. And here we have two counter examples that show us exactly this. For instance, we have S1 here, which is obviously a convex set. We construct here x1 minus k. So it's obviously this point here, it's a minimal point, but it's not true that we can find a supporting hyperplane with lambda strictly positive in R with respect to R plus. In fact, obviously we can construct the supporting hyperplane here, and it's going to be this one. Okay, and so x1 is minimizing the vertical hyperplane. Okay, but this vertical hyperplane is associated to lambda 1 0. Okay, it's vertical. Okay, so so this is the point. I mean, of course we can construct an hyperplane, but the hyperplane is not going to be associated to a lambda which is strictly positive, but it's going to be greater or equal. Okay, so it means that in this case in which we are in R plus, I mean we are doing inequalities with respect to R plus, this means that some of the components are going to be 0. In this case, this corresponds to a vertical hyperplane. And the other statement was the fact that even if x2 is a minimizer of lambda transpose z over, so this is what is written here, over z belonging to the set S with lambda strictly positive in the dual cone. Even if this is the case, that's the point is not going to be a minimal point. Okay, and here we see the example. We see, for instance, that x2 is not minimal. okay? But still, it minimizes it minimizes the hyperplane associated to this lambda, okay? So if we go in this direction, we see that lambda x2 is actually a minimizer for this hyperplane, but the point here is that this hyperplane is not strictly positive, okay? Because we have I mean, it's an horizontal hyperplane, so it's associated to the vector 0, 1. Let's now conclude with an example of optimization problem, multi-objective optimization problem, in which this concept play a role, okay? So we consider a problem in which we need to produce a certain device, a product, okay? And to produce this device, this product, we require two resources. Let's say that the resources are labor and fuel. And the product can actually be manufactured in many different ways, so with different combinations of labor and fuel. And these labor and fuel are resources which are precious, they are valuable to us, and we would like to use as little as possible. So we plot here all the points that produce that are fine to produce a product. So for instance, that means that this combination of labor and this combination of fuel, so this point here, corresponds to a product that can be produced. And also this other, let's say, this other combination of labor and fuel can produce the same product. And of course, we're using more or less the same amount of labor, but we're using less fuel. Okay. So here the idea is that, of course, if there exists this point over here, there is no point in using this because, of course, we are producing the same product, the resources are valuable, and we are using less fuel. And this means that we would like to push this point as down as possible up to here, where we're going to find a combination of labor and fuel that still give us the product, but for which we cannot decrease anymore the amount of fuel, okay? And this is essentially the concept of Pareto-optimal point or efficient point, okay? So a Pareto-optimal point is nothing else than a minimal element of the set P, okay? So the set of minimal elements is called the Pareto-optimal curve, or in this case, the efficient production frontier. Okay. So, in other words, a Pareto-optimal point is nothing else than a minimal point, and the interpretation is that one production method is better than another if it uses no more of each resources than the other method, and for at least one resources uses less. So for instance, if we go back to our figure, we see that this point is optimal, Pareto-optimal, because it uses as much labor as this point and this point, but it uses less fuel. Okay, and there is no point that produces less fuel. There is no point that keeping the labor constant can produce the product with less fuel. Okay, so that it means that this is a Pareto-optimal point. And the way in which Pareto-optimal points can be found is exactly using this geometric interpretation of dual cones. So the idea here is that if we take, for instance, this y transpose z, and we're going to minimize with respect to the inequality induced by the cone R plus, then we're going to go in this direction, and as we push it, we are going at a certain point to find this point over here, which is essentially going to be a minimal point and corresponds indeed with a Pareto-optimal point. So the interesting bit here is that essentially in practice, this lambda can be given an interpretation as the price of a resource, okay? So the idea here is that we have two resources, fuel and labor, and a minimal point is it corresponds to to the minimizer of this lambda transpose x z, where this lambda is a specific price for the resources fuel and resources labor. If you change the price, so if you change lambda, then you're going to end up, for instance, with these different hyperplane. And if we reduce this lambda z, then we're going to end up with another optimal point, probably over here. So you see that essentially we can interpret, I mean, the idea here is that there is no best solution. Depending on the price of the fuel and the price of the labor, there is going to be a solution, an optimal solution, which is Pareto-optimal, and it's a minimal point of the set P. But of course, if you change the prices, and for instance now fuel cost more than labor, then the minimal point is going to, I mean, we're going to find another minimal point, okay? So here the idea is that minimal point, so what is the relation exactly? Well, we talk about minimal points of a set. So we have the set P, and we can identify with this curve that is solid, black solid, as the minimal points, all the minimal points of the set P, and the minimal points corresponds to the Pareto-optimal points with respect to an optimization problem in which we want to minimize our cost. Okay, so you know, I mean, the interpretation of Pareto-optimal and minimal point is different. I mean, one is the minimal point is has to do with a characteristic of a set, while a Pareto-optimal point has to do with an optimization problem. But essentially, they characterize the same elements. This figure here is actually interesting because we can identify some differences between the minimal points that we have here. For instance, x1 is a minimal point that can be identified finding an hyperplane, a supporting hyperplane. x3 also is a minimal point that can be found using a supporting hyperplane, determining a supporting hyperplane. But for instance, the point x2 cannot be, that is minimal, cannot be found using a supporting hyperplane, because you see that if I trace this hyperplane like this, I'm going to cut P, and no matter how I try to pass through x2, I'm always going to cut through chop P. So this is to say that essentially x2 is a minimal point, but as we said, the condition that we have seen based on these supporting hyperplanes is just sufficient, is not necessary, and that means that there are minimal points, and so Pareto-optimal points that cannot be found by tweaking this lambda, essentially. And x2 is exactly a point like that. There are in this graph also other 2 points, which are x4 and x5, but these are just examples of points which are not minimal. x5 is not minimal because if we see, there is going to be this point over here that consumes the same amount of fuel but less labor, and so that's going to be, this is going to be minimal, and this here is not minimal. And then the same for x4. x4 as well is not a minimal point because, again, if we trace the line here, we're going to end up in x2. So x2 is a point that produces that produces the same product for less labor and the same amount of fuel. So x2 is minimal, but x4 is not minimal.